Good morning, student. Let us see the remaining sums in exercise 3.2 question number 5 with visual notation. Prove that twice in bracket a sine square c by 2 plus c sine square a by 2 is equal to a minus b plus c. Let us solve this solution. This question we can solve in different way. Let us see first easiest way. LHS is equal to given 2 in bracket a sin square c upon 2 plus c into sin square a upon 2, isn't it? Now this can be written as a into 2 sin square c upon 2 plus c into bracket 2 sin square a upon 2. We know that 1 minus cos theta is equal to 2 sin square theta by 2. Therefore, we can write here a into bracket 1 minus cos c plus c into bracket 1 minus cos a. We use this formula, isn't it? That is equal to a minus a cos c plus c minus c cos a. That is equal to a plus c minus in bracket a cos c plus c cos a, isn't it? By using projection rule, a b is equal to a cos c plus c cos a. Therefore, a plus c minus b, that is equal to a minus b plus c is equal to RHS. In this way we can prove this. Hence proved. This question can be solved by using sine rule also, isn't it? Solution. Or we will write or solution. Consider LHS. LS in this case also LHS. LHS is a 2 in bracket a sin square c upon 2 plus c into sin square a upon 2, isn't it? Now using sine rule, a is equal to k sin a and c is equal to k sin c, we can write. Therefore, LHS is equal to 2 in bracket k into sin a into sin square c upon 2 plus k into sinus c into sinus square a upon 2. Again, this can be written as k into sin a into 2 sinus square c upon 2 plus k into sinus c into bracket 2 sinus square a upon 2. This can be written as k into sin a into bracket 1 minus cos c plus k into sin c into 1 minus cos a, because sin square c by 2 is equal to this and 2 sin square a by 2 is equal to this, isn't it? That is equal to k into sin a minus k into sin a into cos c plus k into sin c minus k into sin c into cos a. That is equal to, take out k as common. In bracket we have sin a plus sin c minus sin a into cos c plus cos a into sin c, isn't it? Which is equal to k into bracket sin a plus sin c minus this is the expansion of sin of a plus c, that is equal to k into sin a plus sin c minus sin of pi minus b, because a plus c is equal to pi minus b. That is equal to k into bracket sin a plus sin c minus sin b, because sin pi minus theta is equal to sin theta. That is equal to k into sin a plus k into sin c minus k into sin b. Again, by using sine rule, a is equal to k into sin a, b is equal to k into sin b, and c is equal to k into sin c. Put the values, that is equal to a plus c minus b, that is a minus b plus c is equal to RHS. Hence proved. In this way we can prove by using sine rule also, this can be proved, isn't it? Let us see question number 6. Question number 6 we are going to see. Let us solve question. We will solve question number 6 of exercise 3.2. In triangle ABC, prove that a cube into sine b minus c plus b cube into sine c minus a plus c cube into sine a minus b is equal to 0. Proof. LHS is equal to a cube into sine b minus c plus b cube into sine c minus a plus c cube into sine a minus b. This is our LHS. Using sine and cosine rule. A cube sine b minus c is equal to a cube in bracket sine b into cos c minus cos b into sin c. Isn't it? Now a cube as it is in bracket sin b means k into b into by using cosine rule. This is by using sine rule. By using cosine rule, cos c is equal to a square plus b square minus c square upon twice ab minus cos b means c square plus a square upon minus b square upon twice ac into sin c means kc. Isn't it? We will write from here. Therefore, we get a cube in bracket. This b get cancelled. Isn't it? What is remaining? And k in bracket a square plus b square minus c square upon twice a is remaining here. Minus here c get cancelled. What is remaining? K in bracket c square plus a square minus b square upon twice a. Again this is common, a cube upon twice a, and k is also common. In bracket we will a square plus b square minus c square minus in bracket c square plus a square minus b square will remain. Isn't it? Now this a get cancelled, this a square get a cube get cancelled, a square will remain. So we have a square into k upon 2 into a square plus b square minus c square minus c square minus a square plus b square. Now plus a square minus a square get cancelled. Isn't it? So here we have a square into k upon 2, in bracket we have 2b square minus 2c square. Isn't it? That is equal to a square k upon 2 into 2 in bracket b square minus c square. Now this 2 get cancelled. Therefore, a cube sine b minus c is equal to, we have a square k into bracket b square minus c square. Similarly, b cube into sine c minus a is equal to, we have c square k into bracket a square minus b square. p cube into sine c minus a is equal to c square, here c square, here a square will come, and here a cube, here b square will come, and c cube into sine a minus b is equal to, here you will get c square k into bracket a square minus b square. Therefore, put the values. This is 1, this is 2, this is 3. Therefore, LHS is equal to, put the values in LHS here, isn't it? What is a square k in bracket b square minus c square plus b square k into bracket c square minus a square plus c square k into bracket a square minus b square. What is common here? K is common everywhere. K. Take out k as a common. Do the multiplication. A square b square minus a square c square plus b square c square minus a square b square plus c square a square minus c square b square. Now plus a square b square get cancelled. B square c square and b square c square get cancelled. A square c square and a square, that is k into 0, that is equal to 0, which is equal to RHS. Hence proved. In this way we can solve question number 6, isn't it? Remaining questions we will see in coming video.